Good afternoon, everyone. Probably wondering why it was so quiet. So I just turned on the microphone and the recording, so we're good to go. So welcome to microprocessors. And today we're going to talk about servo motors and stepper motors, see some of them in action, and see some of the processes that we use to be able to make this all happen. And so first off, let's just review where we were last time. We saw that we have this function called output compare that we can use to generate pulse width modulated signals. And pulse width modulated signals, we characterize them by duty cycle, where we talk about the percent of the time that the signal is high, the ratio of time high to the period, the time that it takes for the signal to repeat. And so that ratio times 100% is what we call duty cycle, and it's expressed as a percent. So what we want to do is we want to be able to use this to control motors. And so what we're going to do is we're going to set up a signal such that it has a period. In this case, our period is going to be 20 milliseconds, and we're going to vary the width of this time high or the width of the pulse so that we can control the motor. So the motors we're interested in are the stepper motors, and these stepper motors are motors that basically have a limited range of motion. And so the way we control these is we will basically provide them a signal that repeats every 20 milliseconds, and the period of the signal is 20 milliseconds, and the pulse width varies from 1 to 2 milliseconds. We can do this very straightforwardly using the output compare, or if we're going to control a number of motors, then it might make more sense to actually use timers. We talked about using timers to do this, and just to revisit what we're doing with the timers is as follows. So we come over here to our program, and what we're going to do is we're going to use a timer that is basically going to generate an interrupt every 20 milliseconds. So our interrupt service routine in this case is going to be very straightforward. We basically just clear the interrupt flag, and we set another flag so that we know it's time to start the sequence of our timer, sequencing, using the same word, redundant. And so when we set up our timer, we're using timer number 4 for our interrupt or for our delay. So if we want a delay in our program other than our 20 millisecond, we can use timer number 4. And then what we're going to do is we're going to, and this is where we'll get our pulse width, and timer number 1 is going to be used to generate our 20 millisecond interrupt. So what we have to do is we configure it with a prescale such that we can get a reasonably large number in the timer register, and in this case with a prescale of 8, we can have it count up to 61A8 in hexadecimal. We know our max count is FFFF, and so if I prescale it by 4, I could actually get that a little bit higher, but was a little conservative in terms of letting the maximum count, approaching the maximum count. So what we're doing is we basically configure this for interrupts, and now what we're going to do is allow this timer to generate our interrupt signal. So if I fire up the board, then I can actually demonstrate what's going to happen. But before I do that, I want to explain a couple other things. So recall what we're doing is we are now using motors. And so what we need to do is we need to consider the power that the motor takes. And what we're doing is on this MX7 board, we use an additional peripheral module to allow us to be able to do the power conversion. So this has switching transistors that allow us to be able to provide the higher power that's necessary for our motors. So if I'm driving 8 motors, I'm not going to be driving that through the USB port that we use to power the board. So we have to look at how we configure the board a little bit differently. And in fact, I'm going to start up another document here in a second to show you, or I can show you on the board itself. Excuse me. So what we do is we feed in our digital signals, and our stepper motors use a standard 3-pin connector. So if I look at my device here, you see that I have this standard 3-pin connector that I'm going to connect into my peripheral module, and this providing the digital signals. So we provide 3 signals to the servo motor. We have power, ground, and a signal that, and you see right here we have signal, VSS, power, and ground. Those are the 3 signals we provide to the motor. And so we'll be able to connect 4 motors with this, and we have 4 logical inputs that we're going to drive. Those could be output compare, or they could be using the timers, doing them in sequence. And so when we do this, we have to provide additional power, and I think I want to do it this way. So bear with me for one moment. So when I'm using the MX7 board and I wish to provide external power, notice that we have on the board, we have terminals and we have this block, plug-in block that we can use to provide external power. And what that allows us to do is it allows us to be able to, rather than using our USB input, which is shown here on the bottom of the picture, we can now provide a higher ampacity or higher current capacity power supply to allow us to drive the motors. The other thing we can do is we can also switch these jumpers here next to the PMOD connectors, so that we can, instead of using our 3-volt regulated power, we can use our input power to drive those modules, and they can use their onboard regulator to basically regulate it down to 3 volts as necessary. So what we're doing in this experiment, which I'll show you here shortly, is we're providing 5 volts in, and then we are then reconfiguring the jumpers so that we power the modules externally, and then we can power the motors correspondingly. So let's look at actual use of these devices. And so what I'm going to do is I'm going to give you a demonstration with the signals that we're actually going to use. Okay, so here is my project, and let me make sure it all functions properly. And because we're engineers, we want to make sure our signals are actually running properly. And so what you see is I have a pulse that is being repeated every 20 milliseconds. So you see, so here's 0 in the center, here's 20 milliseconds off to the right, and I'm going to change my time resolution because I want to illustrate, and I'll move 0 a little further over here. And in fact, let's get even a little finer. And so I have 0. And so what I'm doing is I'm using my analog to digital converter. And let me change cameras here. So as you can see in the camera view, and I don't know how large you can make this, but what I have is I have a configuration here where I'm using my analog to digital converter. You see it up there on the top of the screen. I'm pointing to it here with a screwdriver, and I'm going to feed that into my MX7 such that I can control the position of this servo motor. So again, a key aspect of the servo motor, as I move in closer and closer, is what I'm going to do is I'm going to control the position. So you see on the screen we have the oscilloscope, and as I try and change this value here, so let's move it all the way to one extreme. So if you see the motor, and of course there's probably a video delay in sampling, but you see that as I change my pulse width, I'll do this slowly so that you can see it. And let's see if I can get a little closer even. And I'll even move the motor over here so that now you can see that. And let me do this. That might also help. So as you observe the pulse width changing from 1 millisecond, so you see the motor is moving to it's moving clockwise, and now it will move counterclockwise as my pulse width increases to 2 milliseconds. And if I go a little past 2 milliseconds or a little less than 1 millisecond, I can get a full 180 movement of the servo motor. So recall, servo motors are intended for applications where I need a limited range of movement. And what I'm doing is I'm controlling the width of this input pulse, the signal pulse you see on the oscilloscope, that allows me to be able to position that armature of the motor accordingly. So servo motors are very useful in applications where we need things like steering and so on. Well, there are a number of other applications where we need a different type of movement, and that's where we use what are called stepper motors. And so what I'd like to do today is show you the difference between the stepper and the servo motors and the way that we control them. So again, the servo motor, what we're doing is we're providing an input signal. We have the three signals. We have our biases, so we have our our power, VCC, and ground, and then we use our signal to basically control the position of the armature or the shaft of the motor. Well, those are very good, like I say, for limited movement applications. But there is another class of motors which we call stepper motors, which we use in many other applications. So before we actually do a demo, I'd like to go through some of the differences of how we actually energize this. So what we are seeing is a number of different DC motors, and stepper motors are DC motors that basically will rotate in a full 360-degree range of motion, but we move them in very, very small steps. And so the way we do that is in the motor itself, we have a number of coils that we will energize in a particular sequence so that we can cause them to move forward or backwards, and we move them one step at a time. And so with these motors, we can do very precise positioning. So for example, in a former life when I worked at Los Alamos, I was designing stepper motor controlled laser fusion mirror position. It was a laser mirror positioning system for laser fusion experiment. And so we had these very large 12, maybe 14-inch mirrors that used three motors to basically position the motor. Could move all of them forward or backwards, or we could basically tilt the motor to position it precisely on the target location. And so with these stepper motors, typically they're connected through gear trains to some movement mechanism. And an example that you probably see repeatedly are things like numerically controlled machines, inkjet printers, any sort of thing where you have precise positioning. Now, the bad news is when I first turn on the motor, it has no inkling of where it is positioned. So it must have some sort of, it needs a way to be able to determine a reference or a datum from which all of the other movement is basically going to be done. And so with these motors, we can do very precise control once we know where we are when we start up. So for example, when you power up your inkjet printer, what's going to happen is you are going to now hear a bunch of noise as it goes through, and it basically figures out where it is, and now is going to, once it figures out its reference, then it's going to be able to continue operation. Okay, so these stepper motors, as I mentioned, are nice in that we can move them in forward or clockwise or counterclockwise directions in very, very precise steps. And so what we want to do is we want to figure out, well, what types of motors are these and how do we control them? And so we see that they're used for a number of different things. We can use them for precise positioning. We can control our rate of speed by either making our pulses faster or slower. So we can do very precise speed control. And these basically are nice because they also have low speed torque. Now, it's a mixed bag because as we have high speed torque, that also means power. And so it's a trade-off between torque and power. So we see right here, low efficiency, they draw power whether they have load or not. So those windings will be energized and holding the system in place. And you'll find that when it's not energized, you can't rotate those shafts. Well, for a couple of reasons, and we'll get into that a little bit. But so in any event, if I'm trying to run a system at real high speed, then again I have the issue of not a lot of high speed torque because they're actually optimal for low speed. And again, no feedback. So I need some way to be able to determine initial position with these motors. Okay, so I mentioned we have phases in these motors, phases or windings in these motors, and so we want to be able to move these in a direction, forward or reverse, and we're going to find that they have internal windings that we have to energize. And there are different styles, and we're going to look, we'll focus on one particular style, but I just want to sensitize you that not every stepper motor is the same, and the way that we drive them varies as well. And so the motors we're going to look at will have a limited number of windings, and what we can do is we can either energize them in a single winding at a time in one direction, or we can have opposite directions. So there are different ways that we can actually run these motors. So if we have a single coil, that means that we're going to basically energize one winding at a time. And so as we cause our armature or stator, well, the armature, as we cause it to rotate, depending on how we're actually energizing those, it's going to either move in a larger or smaller direction, and the torque will vary as well. And so if I just use a... Yes?
Is the armature or the stator the moving component, or is it just depend?
So the armature is a rotating component. And the stator is you could think of that as the housing. And so I'm going to have windings in the, I have windings in the stator. So if I have a magnet in my armature, and then I energize windings in the stator, then what's going to happen is I'll have repelling forces which will cause it to move. So somewhere or other I need to have some magnetism in this system to allow it to be able to move. And if I have windings, if I have slip rings and I have windings on the armature as well, then I can have both. I can have non-magnetic components, but I generate my magnetic field using current through the windings, and so I complicate my design, but I have slip rings or brushes now. So, okay, so we can, for the purposes of this discussion, what we're focusing on is energizing a single winding. And so if I energize a single winding, then I minimize the power, I lower the torque, and as a result, I have less power consumption. I can energize two coils, and I might have them either complement, well, I might have them in the same direction, or I might have them in opposite directions, as you'll see. But the thing is if I'm exciting two coils, then basically I have more torque, I consume more power, but it may be desirable to do that. And I may use what is called a half step. So I will go through a sequence of energizing one winding, then two windings, then one winding, then two windings, and that's the type of mode that we'll be operating in. And the reason being is it gives us higher resolution. And so it makes life a little bit more complicated, but we're engineers, we can handle complications, so we know how to deal with those sorts of things. And we'll see that it's actually not that big of a deal with our electronics. So let's see, there's a question here, how do you control how many coils you generate? Well, the question here is how many coils we energize, not so much that we generate, but so depending on the motor design, it may allow you to be able to energize single coils or multiple coils. And as we look at our systems, we'll see how that actually works. So stand by with the question for a little bit, and then hopefully I'll answer that question. Okay, so if we are looking at this conceptually, if we are energizing in a half-step mode, so notice here I'll just indicate windings here. So I indicate this winding is energized, these others are de-energized. Then when I'm at a 45-degree angle with this, I energize these two windings, A and B, and A prime and B prime are de-energized. Then I go to B. So you see 1, 2, 1, 2, 1, 2, and so on. So we're going to go in this sequence to alternate between one coil and two coil, and this is what we call a half-step coil mode. And so in the half-step coil mode, you see that we energize two coils, and then, well, in this case, we're doing a half-step dual coil, so we're doing two coils, then 4, then 2. So it depends on how the motor is actually designed and built. And this is a more complicated system, this one in this slide, than what we would normally be concerned with. And so what we're interested in is the stepper motors that have this type of construction. In this type of construction, we have two windings, and notice these are bipolar, so I can either have a positive and a negative voltage, so say positive on 3, negative on 4. Similarly, I could have a positive on 2, a negative on 1. So I can alternate the flow of current in these windings, and with the bipolar combination, you can see how I could have complementary magnetic flux that would cause my armature to rotate. However, when I have a bipolar configuration like this, now the circuitry to drive it is considerably more complicated. Okay, so what we're going to look at is a unipolar kind of configuration. And so we have a center tap on these windings, and we have 4, we'll call these ends of the windings. This would be the center, and what we're going to do is we're actually going to tie these two together. So the two center taps of the windings are going to be tied, and current will always flow in just one direction in these windings. And so this is the way that we will actually use our stepper motor. And we see that we have some, I don't want to dwell on the unipolar versus bipolar, but suffice it to say bipolar requires a lot more complex circuitry and has to do with windings and so on. So what we're going to use is we're going to use a 28 BYJ-48 stepper motor that is basically designed for unipolar operation. And let me come over here. And what we're going to see is, in this case, we have 5 wires that come out of our, well, this one has 6, but a lot of them have 5. And so in this case, we see we have these 2 wires tied together. I'm sorry, we have the red, which is going to be our positive voltage, and then we'll have our 4 signal wires. And what you will see is when we're doing our half-step sequence, switching sequence, we're going to energize 1, then 2, then 1, then 2, 1, 2, 1, and then back to 2. And notice the numbers on the windings. So I have 1, 2, 3, 4. And so this interchanging of the windings is important. And with this type of motor, we can also energize it in the following ways. So I can also use a single phase full step. So what I'm going to do is, using my, instead of 1, 2, 3, 4 A, B, C, D, I can energize one winding at a time. So this would be a full step, and recall full step will be less resolution, and also it would be less torque. Whereas if I do two-phase full step sequencing, now what I'm going to do is I'm going to energize two windings in every step. So this again would be full step, so less resolution and higher torque. Okay, so you're probably wondering, well, what's this half step, full step, and so on. So let's look at our motor. Okay, so what this has is this has an internal motor with an internal shaft, and then there's a gear train that basically steps down the rotations of the internal shaft to the external shaft. So if I energize my windings in the half-step mode, I have an internal shaft that moves 5.625 degrees per step. And that, of course, that's a half step. And then I divide it by 64, so that now I have a 64th of 5.625, or 0.09 degrees per step. And so this is a very fine resolution. And so as you see, it takes 4,000 steps to make a revolution. And what I'm doing is I'm energizing them using this sequence. And so what I'm going to do is I'm going to show you how this would actually work using code. And so what I'm going to do is I'm going to use my ports, and I have to use another adapter that is going to allow me to drive the stepper motor. So let me briefly talk about this. So this is another interface that's designed to drive two stepper motors. And we see that it's designed that it has support for two different kinds of windings. One is a 4-pin connector and the other is a 6-pin connector. Well, interesting, because our stepper motors use 5-pin connectors, so we have to do a little bit of jerry-rigging to make this work. So we have the 4 phases for energizing the windings, and on this board, again, we have the provisions for external power to the board directly, but in our case, we're providing that through the board itself. So we're going to basically draw our power from the board and then energize the motor. And we have LEDs on here that will indicate how those windings are being energized. Okay, so this is the device that we use to connect our motors. And you see here's our signals. And so we have the signals for the stepper motor, and then we have diagnostic signals. So what I'm going to do is I'm going to actually energize both the diagnostic and the output signals simultaneously. So let's see how we're going to do that in code. Okay, so a very simple operation. We don't need any interrupts. All we need is a little bit of a delay between each of our steps. And so what I have is I have a timer in there for a delay. And what I'm also doing is I'm also illuminating the LEDs on the MX7, just so you can see, in the event I don't have a stepper motor connected, how those are going to be energized. So what I have now is I basically have an indication of whether I'm moving in the forward or reverse direction. And so I'm going to use a speed term that will basically dictate how fast am I going to sequence through the windings. And so as I go through, what I'm doing is I'm doing the exact same step that I showed you previously. So if I think about the number 8, 8 is 1, 0, 0, 0 in binary, and so I have one winding energized. And I'm doing this on 3 different outputs. So on output G, this is for my LEDs on the onboard, and this 8, is for the 8 ports that are connected to my stepper motor module. And then I go to C. If I look at C, that's 8 plus 4, which is 12. So that's 1, 1, 0, 0. So now I have 2 windings energized. Then I go to 4. So recall C was 8 plus 4. Now I'm down at 4, 0, 1, 0, 0. Then I go to 6, which is 4 plus 2. And you can think of the weights of the bits, 1, 2, 4, 8. And then I go, so here's 6, then 2, then 3, then 1. So this is going in the forward direction. And in the reverse direction, I just go in the opposite direction. And so I go 8, C, oh yeah, so I'm going in the opposite direction. And so what we're going to do is when I execute this, you'll see how this actually works. So let me change projects here. And what I'll do is I'll switch cameras so that you can now see all of the activities. But what I'm also going to do is I'm going to fire up this guy. Workspace. So now what I'm doing is I'm actually energizing these windings. And so let me stop it. And we see that right here I go from, here's the beginning of my sequence. So here's 1, and then here's 2 windings. Here's 1 winding, 2 windings, 1 winding, 2 windings, and then 1 winding here. So I can do this here. I can move it to 0. But you see this is running live, and if I wanted to change my time delay here, I get a little better view there. And so what we want to see is, let me go back to my tools. And I think, Nathan, you might have your mic open. Okay. And so as you can see on this armature, if I can get a little closer maybe. You'll see that if you look at this, it is rotating, but it's rotating kind of slow. And if I look at move this out of the way, here is a sequence that the LEDs are being energized. So you see that, and unfortunately I don't have a zoom with this webcam. So those LEDs that are being illuminated are basically exactly the same as what you see on the logic analyzer. And if you look at the motor, you see that it's rotating very slowly. So let me basically pause this for a moment. I'm going to change my speed value. Let's make this 10. And let's make forward 1. So we change direction, and we'll increase the speed. And of course I could do this all in code, so I wouldn't have to recompile it, but I just haven't done that yet. So now you see that the motor is turning considerably faster. Our windings are being energized at a lot quicker rate. and we can actually make this go faster as well. And so these stepper motors, as we see, we can position very, very accurately. We can control speed very, very accurately, but the way that we energize them is different. So we see that the way we're actually driving those signals is different, and that we're energizing 4 signals simultaneously. And so by doing this, we're able to get a full 360-degree range of motion. And of course, it takes us 4 port outputs to be able to drive this. So if I wanted to drive many motors, then I would need a number of output port signals, which I can do. It just precludes me from using some of the other devices that I might potentially want to use. And so if I change my timing here, and so now I see I have exactly the same sequence. And if I wanted to go faster, I can do that. So let's where's my speed? Here it is. Okay. And so now I'm hoping you can see the fact that it's rotating faster and faster. And let's see if I can even get a little closer without throwing everything on the floor here. And so through this sequence of phases that I'm energizing, and why is this guy flashing? Okay, so you can see that I'm now driving this motor, and these are my signals, and you see that it's getting faster and faster as I'm energizing those windings. Okay, so any questions on our stepper motors or our servo motors? As you start to hopefully appreciate, with this microcontroller, we could actually build our own robotic kind of device. We could connect a multitude of sensors. We can do some very sophisticated processing with it. And one of the goals that I have set for myself is to try and inspire you to want to tinker with these devices. As you start to see these devices all come together and make them work and do things that you need them to do, hopefully you come to appreciate the power of these microcontrollers. And notice that the heart of most of what we're doing is all in one single integrated circuit. So this is a tremendously powerful device. It has lots of flexibility, lots of capability, and of course to interface to some of the devices we need external circuitry, but the capability that we have within this microcontroller is tremendous. Okay, so I'm going to leave it there at the end of the stepper motors. If there's any more questions about stepper or servo motors, please give me your questions now. If not, what we'll do is we'll stop the recording here in a moment, and we will see you on Thursday. Okay, any other questions or issues there? So this is a lot of fun. Sometimes it can be a little frustrating playing with this in the lab, but once you start getting these things to work, you really come to appreciate and derive an interest in doing these sorts of things. So maybe we can work out something where if you're interested in doing some of these labs after the fact, by all means, I would like to invite you to come and do that maybe in the fall semester. And so that's something that you could do if you want to pursue that. Okay, final exam will be available to you on Thursday. It's a take-home exam, and you will have until next Wednesday to turn it in. It's normally with a test that you would do in class for maybe an hour and a half, but you will have a number of days to do it, so no time limit on the test. And so everybody should be able to do very well on it. Okay, well, no further questions, then I'm going to stop the recording, and I will see everybody on Thursday.